Hello, everyone. My name is Charlie from Beijing Institute of Control Engineering. Thank you for coming. I'm going to present our recent research work, precise and efficient atomicity violation detection for interrupt-driven programming via staged path pruning. Interrupt-driven programs are widely used in safety-critical areas, including aerospace, automotive, electronics, medical equipment, and so on. This type of software is usually programmed with interrupts to interact with hardware and respond to external stimuli on time. They generally contain the main task and multiple interrupt slice routines. The preemption of interrupts is non-deterministic. The preemption relationship between interrupts is asymmetric, and interrupts are usually scheduled at a fixed priority without being blocked. Interrupt masking is the processor's only concurrency control mechanism for programming. However, interrupt masking will affect the real-time performance of interrupt response. So programs usually adopt ad hoc synchronization mechanisms, such as flag variable, to control data synchronization. Nevertheless, atomicity violations occur when programs expect multiple related instructions to be atomic. But this expectation is broken due to preemption by the ISR. According to the report and trend, atomicity violations are the most typical and challenging interrupt-related concurrency bugs to detect. 76% of concurrency bugs are atomicity violations in aerospace embedded software. Let me show you a real-world example. The two consecutive local reads, S1 and S2, are expected to read the same value. Nevertheless, when S1 is not satisfied and the value of FGTV28 in S3 is modified after interrupt preemption, then S2 is satisfied. That means the remote write S3 may make the two reads S1 and S2 have different views of the same memory location. It will break the developer's expectations and send an uncomputed value, causing a serious error. This kind of bug can be characterized by access interleaving pattern, which means two consecutive local accesses from one task or interrupt to the same shared variable are unserializable interleaved by a remote access from another interrupt. If such a pattern is violated, an atomicity violation bug will happen. There is some related work. The first category mainly focuses on data rates. However, interrupt-driven programs often use ad hoc synchronization mechanisms. A large number of data races are intentionally designed for data sharing. Most detection results are benign when data races are a detection goal. The second category adopts static analysis or verification for specific atomicity violation patterns. Unfortunately, they cannot achieve simultaneous high precision and scalability. So the challenge is how to precisely and efficiently detect atomicity violations in interrupt-driven programs. Through a large number of real-world cases, we have observed that invisible consecutive local accesses pairs do not lead to atomicity violations. Consider the example, which has three accesses, S1, S2, and S3, to the shared variable YC data, apparently satisfying the WWR pattern. However, the ISR periodically updates YC data at S2, and then sets the flag variable FG at H2 true. The main task is designed to read YC data only when the ISR has just updated it by using the if statement before S3 as an explicit test for the ISR having run. Although S1 and S3 are two consecutive local accesses, they have mutually exclusive and thus they are infeasible, indicating the program has no atomicity assumption on them. Thus, there is no atomicity violation, even if an access interleaving pattern is violated. By pruning such infeasible consecutive local access pairs, we can avoid false positives and reduce the cost of subsequent concurrent path analysis. And the second observation is, it is unnecessary to check all the concurrent paths when feasible interleaving pruning. Naively, we should check every preemption point. This will result in numerous concurrent paths being checked. However, different points may share the same context concerning the shared variables involved in paths constrained expressions. Thus, we can selectively check some representative preemption points rather than all. As the right side shows, we only need to check 3 preemption points to determine the feasibility. So we can reduce the interleaving space significantly. Based on these two observations, our main idea is that more precise analysis is gradually introduced to eliminate false positives. Thus, the higher overhead stage faces fewer violation candidates. The figure shows an overview of our approach, which consists of 3 stages. Stage 1, access interleaving pattern matching. Stage 2, consecutive access pair feasibility checking. And stage 3, infeasible interleaving pruning. In the first stage, we detect all the access interleavings that could cause atomicity violations as candidates. We first identify consecutive local accesses pairs using interprocedural data flow analysis. Then, we compile the interfield access for pattern matching to identify the 3 accesses that belong to the access interleaving pattern. These interleavings are atomicity violation candidates to be checked in the subsequent stages. In the second stage, based on observation 1, if 2 consecutive local accesses are not feasible, then the program has no expectation of atomic execution for them. First of all, we construct the path constraint between each pair based on the dependency graph. Then, we check the path feasibility between each 2 consecutive accesses using SMT solver and filter out infeasible candidates. In the third stage, Interatom analyzes the intermediate results obtained in the previous stage to eliminate the infeasible concurrent interleavings. Based on observation 2, we first construct the symbolic summary of each ISR to avoid redundant path condition computation. Then, propose a representation preemption point selection method to reduce the interleaving space. Finally, checking feasibility by constraint solving. To evaluate Interatom, the following research questions are considered. The first one, how effective is Interatom on detecting atomicity violation for interrupt-driven programs? The second one, how efficient is Interatom? And the third one, how effective and efficient is each analysis stage of Interatom? We run experiments on both benchmark and real-world aerospace embedded software. The real-world dataset comes from the China Academy of Space Technology, and consists of 6 representative software. This table shows the results on response in comparison to our checker. In the Atom can detect all atomicity violations in response. And in the Atom has only 6 false positives out of 31 benchmark cases, which reduces the false positives by 72% compared to our checker. 51 atomicity violations were detected in 6 real-world programs with an average false positive rate of 19.6%. The experimental results demonstrated that in the Atom can effectively detect atomicity violations in real-world interrupt-driven programs with a very low false positive rate. The runtime statistics show that in the Atom can complete the detection of most cases in a short time, with an average detection time of 0.196 seconds, which is 3 times faster than our checker. In the Atom can analyze all examined real-world aerospace embedded software in 135 seconds, which is impressive for industrial applications. To better understand the efficiency and effectiveness of each stage, we pay attention to the number of atomicity violation candidates detected by the first stage, the candidates pruned by the second and third stages, as well as their time costs. The experimental results show that every stage significantly contributes to the overall results. To further evaluate the effectiveness of proposed representative preemption point selection method and symbolic summary, we implemented 2 extra variants in the Atom. As shown in table, both 2 methods significantly improve scalability. In this talk, we mainly introduce in the Atom a static analysis approach for atomicity violation detection in interrupt-driven program with a staged design that makes the detection more precise and efficient. We evaluate it on both benchmark and real-world programs. The result demonstrated in the Atom is promising in providing industrial strengthened capability in atomicity violation detection. In the future, we intend to further improve the precision of our approach. So that's the end of my presentation. Thank you very much.